Hello and welcome. These are the solutions to quiz 25. Use the below reaction and its standard enthalpy change of reaction. How much heat is released when 6 grams of methane completely combusts? Okay, so this is the heat change. This is Q reaction. When 1 mole of methane reacts with O2, it's actually not balanced. You should have a 2 in front of the O2 to form CO2 and water. And so for this reaction, we're trying to figure out perhaps Q reaction, and then from there we can answer the question. So we might take our 6 grams of methane, use the molar mass of methane, so it'll be 1.008 times 4 plus 12.01, so it's going to be 16.04 grams per mole of CH4. Then for every 1 mole of CH4 that reacts, so I just use the 1 mole here, then Q reaction is minus 890.7 kJs. This reaction is exothermic, it's releasing heat. So 6 divided by 16.04 times negative 890.7 is minus 333 kJs. So 333 kJs is released by this reaction. So the reaction loses this much heat, gives it to the surroundings. Perhaps they can warm up. Perhaps they can move. Put the surroundings into motion if this were in a mechanical system. Number 2, the enthalpy of reaction for HCl and NaOH in water is shown. If we have a mole of each solution mixed at 25 degrees C, classify the ensuing reaction as exothermic or endothermic, and identify whether the solution will increase or decrease in temperature. Okay, this reaction is exothermic because of the negative sign on delta H, so we have an exothermic reaction, not an endothermic reaction. Because it's exothermic, our reactants are higher up in enthalpy than our reactants. So the reaction loses delta H. So delta H is less than 0. The reaction's losing enthalpy. That heat given off, or lost by the reaction, is given to the solution that contains the reaction. So the solution should increase in temperature. So exothermic reaction here, and the temperature should increase as the reaction occurs. Coffee cup calorimeter initially contains 125 grams of water at a temperature of 24.2 degrees. We got KBr being added, 10.5 grams at the same temperature, dissolves in the water, leading to a final temperature that drops to 20.90. What is the enthalpy of the below reaction in kJs? So we want to look at this balance reaction. So KBr solid dissolving into water to make aqueous ions, water-soluble IC. The temperature of the solution is dropping, so that's telling us that the enthalpy of the reaction is positive. The reaction is absorbing heat from the solution, so the solution's temperature is dropping. So that helps us rule out D and A right off the bat. And then we can perhaps take our Q reaction. That's ultimately what we want to find to be able to address what delta H is for this reaction. We want to maybe find Q reaction first. It's always a negative Q of its surroundings. The surroundings here is the calorimeter and the solution containing, so it's really the solution. So I'd say the surroundings of this reaction is the solution that contains the reaction. And then that helps us think that the solution is mostly water, so it can be described by the MCS delta T. But we're going to describe this by the MCS delta T of the solution. So the CS turns out to be usually either assumed or close to that of water. So we're given that the CS of the solution is just that of water. And then the M would be the mass of the solution here, so the KBr plus the water. So the KBr, the mass of the KBr and its products can help be in the solution and be part of the mass of the solution here. And so that helps us figure out that we're going to do minus the M being 135.5 with 3 sig figs grams times the CS. I'm just going to write CS here, but I know it's the 4.184 joules per gram degree C. And then the delta T is the final minus the initial. So you got to be careful that this is the initial temperature, the 24.2. The final is 20.9. So we can do 20.90 minus 24.2 degrees C. So let's do that math first. 20.9 minus 24.2. That's a negative temperature drop. So our delta T is negative. So the negative and the negative here will cancel each other out. That'll give the Q reaction a value greater than 0, or a positive value. So we do 135.5 times 3.3 times 4.184 gives us 1,871. That's joules. So we might go to kJs. So 1.871 kJs. Now that's the heat being released just by this particular quantity of KBr reacting. The delta H of our reaction would have 1 mole of KBr reacting. So the last step that we need to account for is that when we go to solve for delta H, we're going to take our Q reaction, and we're going to divide it by the amount of reaction that actually occurred. So we'll divide that by 10.5 grams of KBr. If you imagine there being more KBr present, then this Q reaction would have been bigger within that same ratio. Then all we need to do is use the molar mass of KBr. So that'll be 79.9. Let's get my periodic table open. So we'll have 39.10, 39.1, 79.9. So that'll be 119.0 grams per mole of KBr. And this balanced combustion reaction has 1 mole of KBr in it. So moles, grams cancel, we get units of just kJs. So we do 1.87, divide by 10.5, multiply by 119. Let me do that one more time. 1.871 divide by 10.5 times 119.0 gives us 21.2. 21.2 kJs. And that's answer E. Okay, so the key of this problem is that the Q of the reaction, negative Q of the surroundings, this is a fundamental relationship that we shouldn't forget. Heat of the reaction is opposite of its surroundings. The surroundings is best described as being the solution. The solution has a given heat capacity. We know the mass of the solution from the given information and the delta T. So we calculate the heat released, but that's only by the reaction of 10.5 grams. We then have to convert that 10.5 grams over to moles for our heat per mole, and then we use the 1 mole of KBr in the reaction to give us just units of kJs. Okay, number 4, we're given the specific heat of bromine is 0.226 joules per gram Kelvin. How much heat is required to raise the temperature of 10 milliliters of bromine from 25 to 27.3 degrees C? We're given the density of bromine is 3.12 grams per milliliter. So the number of grams of Br2 here would be the 10 milliliters. That's usually how we think of measuring out a volume of a liquid. 3.12 grams per ml gives us 31.2. Simple math, but just making sure I don't screw it up. 10 times 3.12 is 31.2 grams, not milliliters. So that'd be grams. And then from there, we're going to use the Q is equal to MCS delta T. So to raise the temperature of a substance, we have to add heat. And if we wanted to drop the temperature, then we would have to take heat away. Okay, so we might plug in here. We want to know the heat required. So we're solving for Q. So we're just plugging in the mass, 31.2 grams. The specific heat is 0.226 joules per gram Kelvin. And then we're going to multiply by the temperature difference of 2.3 Kelvin. 2.3 Kelvin, and the difference of temperature is the same difference as 2.3 degrees C. Don't let that confuse you here with the Kelvin unit. If we convert both of these, think about converting both of them to Kelvin, then taking the difference, you get 2.3 Kelvin. Keep them in degrees C, you get 2.3 degrees C. So a difference in temperature in Kelvin is equal to a difference in temperature in degrees C. So we just do 31.2 times 0.226 times 2.3. I get 16.2 joules. Standard enthalpy of solution of sodium hydroxide in water is minus 44.4 kJs per mole. When a 13.9 gram sample dissolves into 250 grams of water in a coffee cup calorimeter, how much should the temperature increase by? We're assuming the specific heat of the solution is that of water. Okay. So first things first, let's think of, maybe, I don't know if we have to think of the reaction. This is just saying sodium hydroxide solid dissolves into its ions in water, and the delta H would be minus 44.4 kJs. There's a 1 mole of sodium hydroxide, so minus 44.4 kJs. And so per mole of sodium hydroxide, minus 44.4 kJs per mole. Okay, so if we want to know the final temperature here, we might come back to our Q reaction is the negative Q of our solution, and the Q of the solution is the M solution, CS solution, delta T of the solution. And the idea here is we can calculate what the Q reaction should be, how much heat the reaction should be changing by, because we're given the enthalpy of solution of sodium hydroxide. So our Q reaction, we can calculate this and say, okay, if we have 13.9 grams of NaOH, and that would be 22.9, so say 23.00 plus 16 plus 1.008, that's 40.01 grams per mole of NaOH, and then we're multiplying by 44 minus 44.4 kJs per mole. Moles cancel, grams cancel. We get the heat released. So 13.9 divided by 40.01 times 44.4 is minus 15.4 kJs. So it's relatively important that we keep the minus sign here and this minus sign, because we're saying minus 14.4. And let's go to joules. So let's say 15,400 joules. And the negative is equal to minus M CS delta T. And so that would be minus 15,000 joules. So the minus sign here cancels. So our final temperature has to be higher. The solution should be warming up, which makes sense because this is an exothermic reaction, should warm the solution. So I could take 15,400 and then divide that by the mass of the solution. The mass of the solution is 200 and... Say hello to my cat, everybody, if you're listening. Yay. 263.9 grams. So we'll divide that by 263.9. And then we will divide by the specific heat of the solution, 4.184. And that gives us a delta T of plus 13.97 degrees C. So the temperature is going up by about 14 degrees from the initial temperature. So that should be going up to 37.0. So this problem is kind of the direct inverse of number 3 above. Instead of solving for the Q reaction and determining delta H, we can be given delta H and a quantity and work out the delta T. Number 6, which statement is true? A reaction with a negative enthalpy change is exothermic. That sounds true. For a reaction occurring in a closed system, delta E and delta H must be equal to each other. That is false. Only for a reaction occurring perhaps in an open system might you be able to make that claim, but but that is not true necessarily for a reaction in a closed system. An open system can exchange matter and energy with its surroundings. That is the definition of an open system. It's just an open container, a beaker, so you can exchange heat and matter with the surroundings. And then neither delta H nor delta E are state functions. That is wrong because they are both state functions. So these are both state functions. Q and W, the sum of them is equal to delta E. So the sum of them together is a state function, but each individually we could have any magnitude of heat or work we could imagine being done for a reaction. So Q and W are not state functions, but delta H and delta E are state functions. State functions are useful because if we know a state function for like an A to B, then we can simply flip it for B to A. If it's not a state function, we may not know if we can simply flip the magnitudes of signs if we flip a reaction if they are non-state functions. So it should just be 1 and 3 are true. That's A. Given the reaction, what's the enthalpy change? So we're flipping the reaction, so we flip the sign, and then we're cutting the coefficients in half, so we multiply by minus a half. So it should be about minus 90. And then given this information here, can we solve for delta H? This is Hess's law. So we're just going to do some rearranging. I'm going to go ahead and hit pause and solve the problem and then explain it real quick once we come back. Okay, so what I had to do was take the first reaction as is. I didn't make any changes because I picked up that I have 2 NF3 on my reactant side and I have 2 NF3 on my reactant side here. So that's good. And I don't have NF3 in any of the other 2 reactions. So that's helpful. So that's what I did first. The next thing I noticed was that that my overall reaction I'm trying to figure out the delta H of does not have NOF in it. And I have 2 NOF right here. So I have to get rid of those 2 NOF on the reactant side. And I see my second reaction has NOF, but on the product side. So I have to flip the reaction to put NOF onto the reactant side, and then I have to double all the coefficients. So I'd be multiplying the delta H of that second reaction by minus because I'm flipping it, and 2 because I'm doubling the coefficients. So I go minus 2 times minus 156.9. And so now my 2 NOF would cancel. Let me actually do that with red. So 2 NOF will cancel. And then lastly, I noticed that I have copper solid on my reactant side. I have copper solid on the reactant side here. So I take my second reaction, or my third reaction as is. That helps me cancel out the F2 as well at the same time. And so now we also are canceling out the 2 NOs from both sides of the reaction. So now this sums up to be 2NF3 plus copper solid goes to N2F4 plus CuF2. And the delta H, now since I've manipulated these delta H's, 2 of them I actually kept the same. I might call this delta H1 now, this delta H2, and this delta H3. If I can add the reactions up, the new reactions delta H is just the sum of the individual delta H's. But as the reactions were manipulated, so I do minus 82.9 and then plus 2 negative times 156.9 negative. Just do the math very intentionally. Just do minus 82.9 and then minus, they keep doing the plus, but then minus 2 times minus 156.9. You could also realize that this would just be a positive quantity, so you're just adding 2 times 156.9. Don't let the math confuse you on this because it should be pretty straightforward. And then plus minus 531.0. And these were all kJs in case that was confusing. And so let me try this one more time. So 82.9 negative, and then plus 2 times 156.9, and then minus 531. So I get minus 300.1 kJs. All right, so that's the solutions for this quiz. Have a great day.